Yes, well, let me introduce you first.
Okay.
Welcome, everybody, to another session of the webinar on differential geometry, AmSur-AmSul. I'm Adrian Andrada. I'm speaking on behalf of the organizing committee, Paolo Piccione, Enrique Sa, Juliet Saavedra, also here. And well, our speaker today is Luigi Vezzoni from the University of Torino. He will speak today about the Calabi-Yau problem in HKT geometry. Welcome, Luigi, and thanks again for accepting our invitation. And now, well, if you want to share your screen.
Okay,
Thanks.
okay. Okay, so I hope you see my screen, my presentation, and so
yes,
I hope everything will smooth with my internet connection, which is not very good because I am at home. So anyway, thanks a lot for this invitation. So I'm really happy of having this talk here. And so thanks to the organizers for inviting me. And my talk is in something called HKT Geometry, which is related to the geometry of special Hermitian metrics on complex manifolds. And I'm studying the Calabi-Yau problem in this setting introduced by Alesker and Verbiskiy. And I am at the beginning of a research project with a PhD student in Torino. The name is Giovanni Gentili. And so this talk is about our first results and also about our research project and towards a conjecture which I recall during the talk. Okay. So in the first slide, just the basic definition I consider in this talk. So I denote by capital M a smooth manifold having a real dimension 4n. And on a four-dimensional manifold, one can consider something called hypercomplex structure, which is a tripole of complex structures, which here are denoted by IJK. And this complex structure satisfies the Quaternionic relations. So the first one anti-commute, and the composition of the first one with the second one is the last one. And I mean, hypercomplex structures are studied, and for instance, there is an important result by Obata in 1955, and Obata proved that on a hypercomplex manifold, there is always exists a unique connection called the Obata, today called the Obata connection, which preserves the hypercomplex structure, and its torsion is vanishing. So preserving the hypercomplex structure means that I, J, K are all parallel with respect to this connection. And this connection always exists, and it is unique, and is often good for having information about the manifold. And for instance, there is this first result, which is very useful. And I mean, what happens when the curvature of this connection is 0? This case corresponds to the case where the hypercomplex manifold is locally isomorphic to the quaternionic vector space Hn. And this case is called in literature locally flat. So if I want to understand if I can think my manifold as locally as open set in Hn, I have to compute the curvature of my connection. And another interesting result is what happened when the holonomy of this connection is contained in S, L, and H. Also, this case is interesting because it implies that the canonical bundle of Mi is holomorphically trivial. So this condition implies that we can find on M a complex volume form, complex with respect to I, which is holomorphic. And the converse is not always true, but as we will observe in the next slide, it's, for instance, true if the manifold is HKT, which are the hypercomplex manifolds, which I will consider during this talk. And when the holonomy of the Obata connection is contained in S, L, and H, the manifold is usually called an S, L, and H manifold. Okay, now I can talk a little bit about hyperhermitian metrics. So I consider a hypercomplex manifold, and I consider a Riemannian metric on my manifold. And the metric is called hyperhermitian if it is compatible with each ijk. So if I consider a metric of this kind, since it is compatible with each ijk, every pair Gi, Gj, and Gk induces a Kahler form, which here is denoted by omega I, omega j, omega k. And of course, these three forms are real and skew symmetric. And we can consider this form, which here is denoted by capital omega, which is obtained by considering omega j plus I omega k. What happens is that this form capital omega is always of type 2-0 with respect to I. And this because I and j anti-commute, also I and k anti-commute. And also this form has some nice properties, two nice properties. The first one is that this form capital omega satisfies a condition called the Curial condition. And this means that if we consider the action of the second complex structure on omega, we obtain a form which is of type 0-2 with respect to I, since I and j anti-commute, but we exactly obtain omega bar. So Curial means that j omega is exactly omega bar and also satisfies a positive condition. So if we consider omega of z, j, z bar, for z, which is a vector field of type 1-0 with respect to I and is not 0, then this is always a positive number. So it satisfies a closed condition and a positive condition. And it turns out by using some, basic linear algebra, if we have a form capital omega which is of type 2-0 with respect to I and satisfies these two conditions, then omega determines G by this relation. So 2 times G of z bar is exactly omega of z jz for every z of type 1-0 with respect to I. And so these, sorry, okay, for maybe the situation is solved. Okay. And so this means that omega determines G. And so instead of considering an hyperhermitian metric, we can consider a form omega which satisfies these two conditions. Okay, in order to introduce HKT structure, I have to recall the definition of Bismuth connection. And the Bismuth connection is a connection which is possible to introduce in every Hermitian manifold. So there is an important theorem of Bismuth on 1989, which states that if we consider Hermitian manifold, which here is denoted by MIG, then there always exists a unique connection, which is called the Bismuth connection. Here is denoted by nabla I, such that it preserves the Hermitian structure. And there is a condition on the torsion in order to have the uniqueness, and it satisfies this condition on the torsion. So if we consider T, the torsion of the connection, and if we consider the composition of G and T in this way, we always have a skew-symmetric form. So this tensor here is, of course, skew-symmetric in the first two entries, but the condition is that it is skew-symmetric also in the last entry. And the Bismuth connection is extremely useful in, for instance, in physics, and it's, I mean, Bismuth introduced this connection by geometrical reasons in order to have an index theorem for non-Kähler manifolds, but it's extremely useful in physics, and it seems that it's very used in some physical theories. And of course, if we consider an hyperhermitian manifold, then every ijk induces a Bismuth connection, which here is denoted by nabla I, nabla J, and nabla K. And at one point in 1996, Owen and Papadopoulos need to have an hyperhermitian manifold where the three Bismuth connections agree. And they consider this manifold, and they called them HKT. So HKT means hyperKahler with torsion. But I mean, the terminology is a little bit misleading, because hyperKahler with torsion means less than Kähler, not more than Kähler. So these manifolds traditionally are not Kähler, in the sense that the metric G is not Kählerian with respect to any one of these complex structures. Anyway, they consider this manifold, and they consider hyperhermitian manifold, and they need to have this condition.
Luigi, can I ask you something?
Sorry?
So does this condition mean that the hyperKahler, that the hyperhermitian structure is integrable as a G structure? Is that what it means? Because you could have some torsion, right? But it still asks if the structure is integrable, and that would be natural.
I don't think so. I mean, I don't think that I mean, this condition means that you mean the SPN structure is integrable.
Yeah, like you're asking that your torsion is totally antisymmetric.
Yeah,
right?
Yeah. I mean, yeah, you have this connection, and you ask that the torsion is totally antisymmetric for every connection. But I don't think that this implies that the SPN structure is torsion is integrable.
It could be the opposite, right? It could be the opposite. It could be maximally non-integrable, right?
Yes, I think so. I think it would be the opposite.
Okay, so that makes sense as well, right? You're asking that is,
yeah.
If the torsion was symmetric, then you'd say it's integrable, right?
Yes.
And then, okay, so you're asking the opposite thing. In some sense, this is maximally non-integrable.
Yeah, but it can also integrable. I mean, for instance, if your manifold is hyperKahler, then you can take as connections the Levi-Civita connection. And in this case, you have integrable.
Okay.
So I don't know exactly how to relate this condition with the integrability of the SPN structure. But yeah, maybe there is some relation, but maybe a little bit subtle.
Okay.
And here I put this sentence that, I mean, they introduced this HKT structure in order to study some physical theories, and here there is the name. This is just name for me. I took this sentence from the abstract of one paper, but just to to show that the structures have a role in physics. And at one point, Grancher and Poon prove that the HKT condition can be expressed in terms of the hyperhemission form capital omega that I introduced before, and is equivalent to require that capital omega is D-closed, where this partial is the D operator with respect to I. And this is the usual definition that people are considering today in hyperhemission geometry. So they call the Hkt manifold a hyperhemission manifold such that the form omega is D-closed. Okay, so this is the definition of which I assume during this talk.
I'm sorry, the form omega was already holomorphic?
No.
No, okay.
No,
I see.
it is almost never holomorphic.
Okay, thank you.
Actually, if you have HKT and the omega holomorphic, you have HyperKahler.
Yeah. Okay, thank you.
Okay, and there is a general theory about HKT structures, and here I recall some important results. The first one is due to Verbiskiy, and he developed a Hodge theory on Hkt manifolds. And here I recalled a little bit the definition of this kind of Hodge theory. And so assume to have a Hkt manifold. And then we have a natural action of SU2 on P forms. And then, the actions of SU2 are classified with the weight. So one can consider inside the space of P forms the maximal SU2 subspace corresponding to the weight P. And this space is unique. And by definition, if you consider D is the de Rham operator of lambda P plus, this is always contained in lambda P plus 1 plus. And so we have a de Rham complex corresponding to the HKT structure. And we can do even more if we consider the complexification of the spaces lambda P plus. The complexification is compatible with the splitting of complex P forms in forms of type RS. And so we have a Dolbeault complex corresponding to the HKT structure. And also we have the splitting of D in two operators, which here are denoted by D plus and D bar plus. And if the manifold is SLNH, which means that the canonical bundle of MI is holomorphically trivial, then we can do a little bit more, because there is a canonical isomorphism between lambda RS plus forms into R plus S, 0 forms with respect to I. And so this Dolbeault complex, which is defined here, corresponds to a Dolbeault complex in forms of type P0 with respect to I. And when we regard these two operators in this new complex, the operators D plus is just the usual partial operator with respect to I, while D bar plus corresponds to an operator which here is denoted by dj, and dj corresponds to j to the minus 1 D bar j. So the key point is that since j anticommute with I, this dj increase the first degree of the form of 1. And so we have a new Dolbeault complex in forms of type P0. And I mean, these two operators satisfy some the same relations that we have in the Dolbeault complexes. So D square and dj square are 0, and DJ and D commute. And
Can I
so,
ask a question just related to Gonzalo's comment?
yeah.
Is it fair to say that the torsion is in fact del bar omega?
Yes. Yes.
Right.
Yeah. I think so. Yeah.
Right. So then what this means is that then it's also del bar closed. Therefore, when omega is closed, and then it's torsion free, and then you get an actual hyperKahler.
Yeah, I think so. Yeah.
That fits in.
Okay, and so we have this complex, and so we can define adapted Dolbeau cohomology, which is sometimes called a twisted Dolbeau cohomology. Which is corresponds to the HKT structure, and so you can use this for constructing some invariants. Okay, another good stuff about Hkt manifold is that this condition here can be reversed in the case of Hkt manifolds. And indeed, what we have is that the canonic is that if we have an Hkt manifold, then the canonical bundle of omega I is holomorphically trivial if and only if the holonomy of the Bata connection is contained in SL and H. So in the Hkt case, the holonomy of the Bata connection controls the how much the canonical bundle of Mi is holomorphically trivial. And we have a pluripotential theory in HKT geometry. And the first observation is that any HKT form can be locally written as ddjv for some smooth function v. And so this is analogous to what happens in Kahler geometry, that any Kahler forms can be locally written as dd bar of some potential. And here is the same, where we replace the rule of the Kahler form with this form capital omega, and we replace the two operators dd bar with ddj. Okay, and from this, it's very natural to introduce what is called the space of Quaternionic plurisubharmonic functions, and it consists in the space of function, smooth function on the manifold, real function, such that if we consider the form omega plus ddj phi, we have something which is positive in the sense I explained before. So for every phi in this space, we have this omega phi is a new hyperhermitian, is a new HKT form, and so we have a new HKT structures. So this space. So every phi in this space induces a new HKT form. And I cite a last result about the existence of an HKT structure on an hypercomplex manifold of type SL2H. And there is a quite recent nice result of Alesker, Alesker and Verbiskiy, which says that if we consider a hypercomplex manifold and assume that the holonomy of the Bata connection is in the eight-dimensional case, and assume that the holonomy of the Bata connection is contained in SL2H, then the manifold has an Hkt metric if and only if the first cohomology group of the sheaf of holomorphic functions on Mi is even dimensional. So this is a very nice, very nice recent result. Okay, this slide is about examples of Hkt manifolds. So the first one is a very, basic example is that every HyperKahler manifold is Hkt. In this case, corresponds to the case where the form capital omega is closed. So not only D closed, but also D bar closed. Another interesting result is that every hypercomplex manifold is locally Hkt. So there are no local obstructions for the existence of a Hkt metric. But as we see during the talk, there are some global obstruction on a hypercompact manifold to the existence of an HKT metric.
I'm sorry. Is it okay if I ask another question?
Yes, of course.
So in the previous slide, could you say some words? Why is it that in the HKT case, if the holonomy is contained in SLN, then actually the canonical bundle is holomorphically trivial?
Yes, because so the question is why in this case we can reverse the. So why this result holds? What's the reason?
Because when I saw that, I imagined that it would be something like saying that the Picard group is trivial. But then here on the last item there is an example with H1, so the Jacobian is being given dimensional. I imagine it can be non-trivial. So it cannot be what I was thinking. So I was wondering.
Okay, can I ask to discuss this later? Because
yeah, it's fine, it's fine.
Could be a little bit long and
yeah.
Okay, maybe at the end of the talk, please, if you can. Okay, sorry, but
that's fine.
Okay. Okay, as I said, every hypercomplex manifold is locally HKT, and there is an interesting class of examples coming from a paper of Joyce. I mean, these examples comes from considering a compact semi-simple Lie group of rank R. And what happens if we consider the direct product of G with a torus of dimension 2n minus R? This manifold has always a left invariant HKT structure, such that the metric, once restricted to the Lie algebra of G, is minus the killing form of G. So we can consider compact semi-simple Lie group in order to construct an example of compact HKT manifolds. And this construction can be generalized to homogeneous space, and this was done by Offerman and Papadopoulos in 1998. And other intrinsic examples comes from nil manifolds, so compact quotients of nilpotent Lie groups with lattices, and there are examples of nil manifolds having left invariant HKT structures. I think there are also some classification results due to Dotti and Fino, and some structure results due to Barberis, Dotti, and Verbiskiy. And there are some very intrinsic results due to Swan, and I mean, this is I mean, a little bit involved. I mean, not simple. This is not a simple construction, but using this machinery called the twist construction, it's possible to construct also simply connected examples. And the starting point for constructing this example is considering a manifold having a torus action. And the last item is that there are examples of compact hypercompact manifolds without HKT metrics. And the first one was found out by Grancher and Fino in 2004. And I mean, they proved that on some hypercomplex nil manifolds there weren't HKT metrics. And they obtained the proof in two steps. In the first one, they proved that they weren't left invariant HKT structures. And then in the second step, they proved that if they weren't left invariant HKT structures, then they weren't HKT structures at all. Okay. Okay. And now what I would like to do is introduce the Calabi-Yau problem in HKT geometry, and this can be introduced from several points of view, but I like this point of view because it relates the Calabi-Yau problem with the existence of balanced metrics. So I recall that Hermitian metric on a complex manifold is called balanced if its fundamental form is co-closed instead than closed like in the Kahler case. And I mean, balanced manifolds are extremely important in Hermitian geometry, and here there are some results about balanced metrics. So I think that the first important results about balanced metrics was by Michelson in 1982, and she proved an obstruction for the existence of balance metrics, and she characterized the existence of balance metrics in terms of currents. And this was the analog of a theorem of Harvey-Lawson in Kahler geometry. And from the theorem of Michelson, for instance, it follows that the Calabi-Yau manifolds have no balance structures. A very important result about balance geometry is from two Italian mathematicians, Alessandrini and Bassanelli, and they proved that the modification of a balanced manifold is always a balanced manifold. What is known that, I mean, in general, if you consider a Kahler manifold and we try to modify it, is not always we obtain a Kahler manifold. I mean, if you consider some simple modification like the blow up, then it's known that the blow up of a Kahler manifold, for instance, at one point is always a Kahler manifold. But if we consider a more difficult modification, is not always true. But the class of balance metrics is closed under modification. So, for instance, if we modify a Kahler manifold, we always obtain a balance manifold.
Luigi?
Yes?
What's a modification?
Modification means that the two manifolds are biolomorphic outside the analytic set.
Cool.
So, something more general than the blow-up. And another good result is about existence of balance metrics on twistor space over four-dimensional Riemannian manifolds. And I think this is a result of Gudushan. And it's known that if we consider a four-dimensional Riemannian manifold oriented, and if the metric has some properties, then we can construct the twistor space, and the twistor space a complex structure. And the twistor space is almost never Kahler, but by a result of Gudushan, it always has a balance structure. And also there is a link with the theory of calibration of Harvey-Lawson. What is true that the balance metric is, if we consider a balance metric, if we consider a fundamental form, then omega to the n minus 1 is a calibration, which means that it's closed and satisfies an open condition. And so in particular, it's possible to using balance metrics in order to study minimal submanifolds.
Sorry, isn't the twistor space of ASD4 manifold 6-dimensional?
Yeah, but here I'm speaking about balance geometry, not only balance. Yeah, this is an introduction only for balance metrics. Yeah, it's true. It's not a balance HKT. This is only balance, just to it's true, it's a 6-dimensional. And the last one is that if we have a balance metric, then we can consider the three Laplacian. And it's known that in the Kahler case, these three Laplacians are essentially the same for forms. But what happens on a balance manifold is that the three Laplacian are the same at the level of functions. And so an HKT metric is called balance HKT if it's both HKT and balanced. Okay. So what about the existence of HKT balance metric? And there is a nice result of Verbiskiy, which says that if we consider an HKT manifold, then the metric G is balanced if and only if the form omega satisfies this condition. So its top power is D bar closed. And so what is more or less always possible in HKT geometry is impose extra condition on the metric, and then regarding this extra condition on the metric as extra condition on the form. And here is very nice what happens, because the G is balanced if and only if omega to the n is holomorphic. So in particular, if we have a balanced HKT manifold, then the canonical bundle is holomorphically trivial, because omega to the n is a trivialization of the canonical bundle. And so far, all the known examples of compact HKT manifold with canonical bundle holomorphically trivial have a balanced HKT metric. And so it's quite natural to conjecture that a compact HKT manifold with canonical bundle holomorphically trivial has a balanced HKT metric. So, I mean, this is the geometric. I mean, this is a very geometric conjecture. In the next slide, I put in relation this conjecture with a Calabi-Yau type problem. So what is a possible strategy in order to handle this conjecture? So assume to have a compact SL and HKT manifold and fix a holomorphic volume form theta. So holomorphic with respect to I. And then we consider this, Calabi-Yau type problem. So omega plus ddj phi to the n is equal to a theta, where here phi and a are the unknowns, and the phi is a smooth map, and the a is a positive constant. And then we require that omega plus ddj phi is positive. And in view of the previous slide, if you have a solution of this equation, then we have that omega plus ddj phi is a balanced HKT metric, induce a balanced HKT metric, and this is a good motivation for focusing on this problem. And of course, this form, we can write this form theta as e to the f omega n, where f is a smooth map. And then we can introduce what is called the Quaternionic Monge-Ampère equation, which is the equation given by, which is the equation displayed here. So omega plus ddj phi to the n is equal to a e to the f omega n, and omega plus ddj phi is positive. And the conjecture, this is a conjecture by Alesker and Verbiskiy, is that if, for any choice of the function f, this equation has a unique solution. So this problem is open, and this is the central subject of this talk. So from now on, I speak only of this Calabi-Yau type problem in HKT geometry. And the first observation is this equation is elliptic, because if we linearize the equation, we obtain we obtain this operator. So we obtain ddj phi wedge omega to the n divided by omega n. And this is something I call the Quaternionic Laplacian, and this is a strong elliptic operator. So this is an elliptic problem like the...
What is the geometric meaning of this function f that appears here?
The function f, you mean this one?
Yes.
It's the rate between the volumes.
Yeah, no, but where does it come from, the problem?
Yeah, because you can write theta as e to the f omega n. This is the link.
Yeah, I see.
You need to start with the given holomorphic volume form, but then you can always compare it to this sort of standard.
Yeah. So this is the link between theta and
okay.
It is this new reformulation of the problem.
Okay.
Okay, and what's the local model? If we assume, if we consider this space, this problem in an open set of a Hn, and we can identify Hn with R4n with the tree standard, with the standard hypercomplex structure, and we consider the Euclidean metric on H to the n, then we have two, I mean, these two operators are called Quaternionic derivatives. And here I, j, k are the quaternion numbers. And these are derivations on the ball, and they commute, like the standard derivations. And if we consider the equation, then the equation in this case becomes the determinant of the identity plus something which is called the Hn, the quaternionic Hn of the function. And so in this case, the problem takes the same expression of the complex Motion-Pair equation. And this local version is completely understood by Alesker. But the problem is that when we have the problem in HKT geometry, in an HKT manifold, the problem doesn't look like this even locally, because we can consider cases where the manifold is not locally trivial. So we can't identify the manifold with open sets in Hn. Okay, I have to go more quick. And here there are some known results about the quaternionic Motion-Pair equations. Here there is the list of known results. So the first one is that solutions are unique. And this is that was done by Alesker and Verbiskiy. And the second one, of course, the natural approach for solving the equation is to try to imitate the Yau's proof of the Calabi conjecture. And so the hard step are the a priori estimates. The C0 a priori estimates is done. And it's done by Alesker and Verbiskiy in the special case of SLNH manifold, and then it was proved also by Alesker and Shelutkin in the general case, and then Rocca simplified the argument. Okay, but so the C0 estimate is understood, but the other a priori estimates are still open, and but these estimates are proved in some special cases. For instance, Alesker proved the C2 estimates in a very special case. In the case where the manifold is locally flat, so in the case where locally the manifold is open set of Hn, and in the case where the manifold admits an hyperKahler metric. So when Alesker proved the C2 estimates under these two assumptions. So the hyperKahler metric is not necessarily related with the starting metric, but it is compatible with IJK. And then in the same paper, Alesker proved that if we have the C2 estimate and we are in the locally flat case, it's possible to obtain all the other estimates. So putting these two items together, we have that in the locally flat in the locally flat case, and if we also assume the existence of the Kahler metric, then the equation has a unique solution. And very recently, Dunius Rocca proved another interesting result about the solvability of the equation. They proved that the equation can be solved if the starting metric is hyperKahler. So they drop the locally flat assumption, but they need to assume that the starting metric is hyperKahler. And the problem is not easy even in this case. But this result is very new, is something like 2 weeks. Okay, and now there is our contribution. And so actually we did two different researches. The first one is about the equation and some explicit examples. And we start from 8-dimensional nil manifolds. And fortunately, 8-dimensional nilpotently groups, non-abelian, and carrying a left invariant Hkt structure are classified. And there are just 3 models which are given which are these three models. So each one is the product of a Heisenberg-Lie group with some Rn. In the first case, we have the 5-dimensional real Heisenberg-Lie group. In the second case, we have the 3-dimensional complex Heisenberg-Lie groups. And in the last case, we have the 3-dimensional Quaternionic Heisenberg-Lie group. And what happens is that since we have some nil manifolds in all the cases, we have a co-compact lattice, so we can consider the quotient in order to have a compact manifold. And in these three examples, there is a canonical choice of a left invariant HKT structure, and since it is left invariant, this HKT structure induces an HKT structure on the quotient. So we have a compact manifold with an HKT structure. And it turns out that this manifold has the natural structure of a torus bundle over a torus. And actually, we have the structure of a principal torus bundle over a torus. Yes, and the fiber is a 3-dimensional torus, and the base a 5-dimensional torus. And it's quite natural to try to study the equation in this case when the datum f is invariant by the action of the fiber. And actually, we prove that under these assumptions, the equation is always solvable. And I mean, the key fact here is that if we assume that f is invariant by the action of this torus, then the equation can be regarded as an equation on the base. So we have a downgrading of the variables, and also the equation when we go on the base is, I mean, as simple enough in order to be solved. Okay, here is I mean, very quickly, the idea of the proof. So first of all, these manifolds are locally flat. So by using the theorem of Alesker, it's possible to, so it's enough to prove an upper bound for the Quaternionic Laplacian of the solution. And on the base, when we regard the equation as an equation on the base assume there's explicit formulation on the 5-dimensional torus. So from now on, we can forget everything about HKT geometry and just look to this equation on the torus, which is an elliptic equation. It's not a real Mojan-Pair type equation, but it's very similar. I mean, and the technique for obtaining the C2 estimate is quite standard. It consists on applying the maximal principle of a function constructed ad hoc. Okay, and what happens is in some of these examples can be, I mean, the base can be considered a T6. So in this case, we have more variables here, but the equation becomes too involved, and I mean, we can't handle in this case. So in some case, in some sense, I mean, consider the base 5-dimensional is the simplest case where our machine works. There is an observation here, and is that if we assume that f does not depends on the variable x5, then this part is 0, because I mean, here we have we use the ansatz that phi does not depend on x5, and this part reduces to 1, and here we have the Laplacian. So in this case, which from the geometric point of view corresponds to see the manifold as a 4-dimensional torus bundle over torus, we have that the equation reduces to the standard Poisson equation. So in this case, the problem becomes trivial. And I mean, we go on a little bit from this observation by considering the more involved case. and by replacing the structure of torus bundle with the existence of a foliation. So here the foliation is the fiber, and here we consider the general case where we have the foliation, and then there is some compatibilities between the foliation and the HKT structure. And here, I mean, instead of considering the function invariant by the action of the fiber, we consider a basic function with respect to this foliation. And in the general case, this equation modifies to this more, more difficult equation, where we still have the Laplacian at the beginning, but then we have two extra terms. One here is denoted by Q, and is quadratic in the gradient of phi, and then we have something denoted by L, which is linear in the gradient of phi. We are still studying this equation. This equation is, of course, semi-linear because, is linear in the second derivatives. And here we asked to some friends to help us, and we asked to Luciano Mari and Giulio Ciraulo, which, knows this equation better than us. And it's possible to apply some classical results, and we are almost at the end of this research. So we go a little bit farther with our study on torus bundle, and now we have some results on foliated spaces. And it's a natural question, try to understand how much the assumption on the existence of F is artificial. But this F exists in some, natural examples. For instance, on in the Joyce examples, for instance, if we consider SU3, then we have a natural foliation given by this splitting on the Lie algebra of SU3. So the Lie algebra of SU3 can be split in three parts. One is R, one is corresponds to SP1. The last one is C2, and the C2, and here is denoted by F. SU3 has a natural left invariant HKT structure, and this F induces a foliation on the manifold. So we can apply the previous machinery, but here it's possible to do everything in an explicit way. And here we have the equation reduces to this one. So we have the Laplacian, and the linear, the linear part involving the gradient is 0, and we have just the quadratic part on the gradient. So I think that the same machinery can be used to study the equation on other compact Lie groups, but here we are at the very beginning of this study. Okay, the last result I would like to recall, but very quickly because my time is almost over, is we recently tried to introduce a new machinery for studying the equation, and we introduced a geometric flow in order to study this equation. So we consider the parabolic counterpart of the problem, and this is something which is quite natural in the study of elliptic problems in Hermitian manifolds. And this equation, which is displayed here, is the natural counterpart of the original equation to the parabolic setting. Here the unknown is a function phi, which depends on the variable of the manifold and on a real parameter t. And the subindex t denotes the time derivative, and here we have the parabolic version of the problem. So what is the idea here is that if we have a solution of this equation, and the solution is defined for every positive t, then the limit should converge to a solution to the Quaternionic Motion-Pair equation with datum f. And we proved this under the same assumptions of Alesker theorem. So we proved that under the assumption of Alesker theorem, so in the case of locally flat, and if we also assume the existence of an hyperKahler metric, then this equation has a long-time solution, which is defined by phi. So long-time solution means that phi is defined for every positive t. And if we normalize the solution, and I call the normalization by phi tilde, then phi tilde converges in C-infinite topology to a smooth map. And corresponding to the smooth map, there exists a positive constant such that the quaternionic motion-pair equation corresponding to the function f is, the pair phi infinity and a solves the quaternionic motion-pair equation with respect to the datum f. So this is the analog to many other results involving geometric flows in Hermitian geometry. So yeah, I think the first one is the theorem of Zhao about the rule of the Ricci flow in the study of the Calabi conjecture. Then there is a paper of Gill about the parabolic complex motion-pair equation. Then a paper of Sun about the complex motion-pair equation in the almost complex case. And then a paper, the Fong and Todd, about the study of a quite large class of geometric flows in Hermitian manifolds. And here I put the structure of the proof, but yeah, maybe in 1 minute I can describe the proof. I mean, what happens is that the C0 bound on the derivative of phi is very easy. It just comes from the equation without any assumption. And from this, we deduce that the solution phi has a uniform bound on the oscillation of phi on the solution. And now we need the C2 estimate. And for the C2 estimate, we need the extra assumptions. So we need to assume that the manifold is locally flat and the existence of a hyperKahler metric. But when we have the C2 estimate, we can apply a general result in order to deduce all the other estimate. And in this step 4, we don't need the existence of the background hyperKahler metric, just the local flatness of the manifold. And then when we have the C-infinity bound on the solution, it's not difficult to deduce the theorem by using the same argument of Fong's Sturm for studying the Kahler-Ricci flow, based on, in our case, based on an adapted Mabuchi type functional. So a Mabuchi type function adapted to the space of quaternionic plurisupermonic functions. Okay. Okay, I can skip this slide, just the last slide about our current project. So our project is consists now in try to solve the conjecture in the locally flat case by removing the assumption of the existence of a locally flat hyperKahler, the assumption of a hyperKahler metric. This seems to be difficult, but I'm quite positive, and our strategy is try to adopt an argument of Cherrier, the argument of that Cherrier used in order to, to handle the complex motion-pair equation. In order to, the mixing point is the C2 estimate. And then after that, I'd like to do the parabolic version and try to generalize our theorem about our flow in the locally flat case by removing the assumption of the background hyperKahler metric. And I know I don't have an idea how to drop the locally flat assumption general case. Okay, I think my time is over, so thanks a lot for your attention.
Okay, thank you, Luigi.
Okay, now I see the people. I mean,
Okay.
I watched only my presentation for 1 hour, and it was a little bit, yeah.
Okay, thank you for the interesting talk. And so, are there any questions or comments for Luigi?
There are some, maybe not some question in the chat.
No, it was what was a modification, so
Okay, I think I
answered that
at one point, yeah.
And now Enrique, I guess, has a question.
Yeah.
I
was thinking in the standard Calabi-Yau sort of, you can only set up the complex Mongeon pair problem subject to the major obstruction, which is first Chern class has to vanish, right? So is this problem topologically obstructed from the outset? Is there an obstruction, maybe very easy obstruction, or can you set it up?
As far as I know, only under some, only by considering extra assumptions. For instance, in the paper of Soroka-Dinio, where they studied the problem when the initial metric is hyperKahler, they replace the rule of the first Chern class with the first bot Chern class. And this answers to your question in that special case. But I don't know if this can be done in general, or if the first bot Chern class has to be modified. I think that under some extra assumption is possible, but I don't know the general case.
Okay, and now Gonzalo has a question for Luigi.
Yes, so in the analogous problem in the Calabi-Yau setting, the function f that one introduces there, there is a constraint on the integral of the exponential.
If maybe I can explain this point, but I have to. Now I explain this point. Okay. I think you see again my screen.
Yes.
Yeah.
Allora, okay. Also in the Calabi-Yau problem, if you let me find the okay. Where is it? Here. Okay. Also in the Calabi-Yau problem, the classical Calabi-Yau problem, if you want to drop the condition on f, you can put the real parameter a. So the existence of this parameter is exactly for drop the condition on f. So the problem here is that this is not a volume. So if you want to integrate, we have to consider the wedge product with a form of type 0n. Okay, if you have a holomorphic volume, you can consider the wedge product, and then you can integrate, and then you can use the. Okay.
Yes, I understand. This is an N0 problem.
In the general case, maybe you don't have the holomorphic volume, and so you need a statement which is a little bit more general and involves this parameter a.
Yes, that clarifies, I think. But I still don't understand later in your example, in the Snell manifolds, when you assume that it only depends on the 4 coordinates on the base. You have the Poisson equation, and to solve that Poisson equation, you still need the right-hand side to integrate to 0.
Yeah, because my presentation here is rough. When I put the equation in this way, I drop the parameter, and here I have the condition on the integration on e to the f. In this case, I can do this because I have the holomorphic volume.
Okay, so thank you.
In this case, I have the holomorphic volume. I can remove the parameter, but not in general.
Okay, thank you.
Yeah. You know, sometimes the presentations are a little bit rough on this.
No, it's good.
As I said at the beginning, I'm not very good in doing online talks. So,
It was a great talk.
No,
very interesting.
At one point, my daughter entered the room crying, so I'm very sorry about that.
But my graduate students do the same. It's fine.
I'm sorry. I am alone with the children, and I hope they didn't destroy my home. Yes, Adrian.
I have only one question. You say that in the HKT case, when the holonomy of the Obata connection is in SLNH, then the canonical bundle of MI is trivial.
Yeah.
But that happens for every complex structure. In the sphere determined by IJK.
Yeah, in every complex structure in the sphere, yes.
Well, now I have a problem from a long time ago. Do you know if there could be an example of a hypercomplex structure where the canonical bundle for one of these structures is trivial, but for others it is not trivial?
Is it possible?
I don't know. I have been asking that for a long time, and I do not know the answer.
I don't know. Really, I don't know if it's possible.
Because I think that in the SLNH case, if one is has canonical trivial bundle, canonical bundle, and it happens for all of them. But
the question is super clear, but I mean, you know, it's a little bit. I don't know the answers. Sorry,
I don't know what kind of example to look for.
Maybe these joist examples. Right, because on the joist examples, I think you use you increase the rank, so you double the rank, right, by taking products with tori, and then you make all the structures preserve the root spaces.
Okay.
And so there